Yeah, sure. Yeah, that's it.
While we wait for Tomer to reconnect, so I'm delighted to chair today's discussion, and the floor is open. There's no strict format. Any thoughts or questions for the speakers of the day? Please.
So actually, I have a question for Sergio. Hoping that is there. Oh. No, doesn't seem to be the case. So, okay. I don't have a question.
Hey guys, I'm so sorry. I just crashed.
No worries, Tomer. No worries.
Those X fields are killing me. Sorry, Stefan, do you want to go? You want to repeat again, or did you move on?
Well, so we opened the floor for the discussion, Tomer, but we might as well start. Start perhaps with my question to you, which had to do again with the fact that we do have some measurements from real life cosmic rays, and you mentioned large rigidity, and you've got data on that, as indirect as they might be. So I'm a little bit perplexed why the supernova reacceleration efficiency is so poorly known.
The supernova I don't think is that poorly known. I think that the penetration procedure is poorly known because cosmic rays that we're seeing are just from our, most of them are from our galaxy, right? So
yeah.
So the question whether you can penetrate from, I don't know, 10 kiloparsec above the galactic plane into the galactic plane, that I don't know how well we know. And also, by the way, the separation between the perpendicular and parallel diffusion coefficients, those are, I think, there are assumptions that go into determining the two.
Well, people always assume, isotropy in most treatments of the diffusion equation. So actually, this is perhaps a moment for me to advertise. We're looking at cosmic ray transport in Andromeda, and trying to understand what's going on with you. Tomer, you probably seen these papers that advocate an explanation for the large-scale gamma ray emission from Andromeda as coming from dark matter substructure at very, very large radii away. And, we've been just playing around with modeling cosmic ray transport in Andromeda. You can explain that emission as long as you have a much larger diffusion region than we previously thought. Instead of putting this boundary condition of free escape outside your box, if you have a smoothly and slowly changing diffusion coefficients that extends well outside that cylindrical box, then the data from Andromeda makes sense. So anyways, I completely agree with you that we don't really know much about transport, especially outside, outside what we call the diffusion region. Wonderful talk, by the way, Tomer. I really enjoyed it. Thank you so much.
Thanks. Thank you.
And by the way, I might put in the chat, there's brand new results from the eROSITA X-ray mission that has completed their first all-sky survey, and they have beautiful images of the so-called Fermi bubbles in X-rays.
Oh, this I haven't seen. Okay.
Yeah, let's see if I...
What do we learn from those?
Well, we'll see what we learn, but definitely, we learned something about the origin of the GeV emission, and it looks like, it's consistent with some sort of activity from such a star in the past that accelerated cosmic rays, and there should have been an X-ray emission that hadn't been detected until now. So that's, by the way, I think this eROSITA data will be fantastic for dark matter searches, because up until now we had the ROSAT satellite, which had really shitty X-ray data with very poor angular resolution. So I think it's going to be a gold mine.
Nice. What's the ePrint?
I don't know if there is one. I just saw the press release.
Can you send the link? I will.
Yeah, it's in the chat.
Oh, it's in the chat. Okay.
Yeah.
Ah, perfect. Let's have a look.
So, fellas, any questions for today's speakers? Hello,
Sorry,
Joseph.
yeah, there's a new print. I just found it.
I have a question. Is somebody already asking? Okay.
Go ahead,
Hi.
Joseph.
So, yeah, I guess I have a, follow-up question to you, Stefano. I mean, I know nothing about this stuff, but just so entertaining Tomer's possibility that there is a sort of a live milli-charge state out there. So it's basically the I mean, if it's on the MeV scale, it's the most abundant particle in the galaxy, right? And it's electromagnetically active. So I wonder if it actually contributes to the synchrotron spectrum that we observe. I know it's probably all swamped, but is it possible to have a direct synchrotron signature there?
It strongly depends on the. I'm not sure, right? Because it strongly depends on the fraction, right, of these milli-charge particles.
Yeah, so fraction milli-charge, so a double. You say there's a double
on the fraction and also on the charge, right?
Yeah,
right.
Exactly. So a double
emission scales. Tomer, that's an E&M problem I might give to my students. How does the synchrotron emission scale with the charge of a particle? I think it scales quadratically. So you've got an epsilon squared in the synchrotron signal as well, I would say.
Okay.
Right.
What about the mass? What about the mass scaling?
Well, the mass affects the number density, and so there's good news there if you've got a light particle. And of course, there is, the synchrotron emission, as we know well from collider physics, is very sensitive to the mass as well. I think it's a 1 over mass squared.
So that might compensate 1 squared factor.
Probably so, yeah. But that's a good point. I never thought about that.
Given the small density, I still find it hard to believe you'd be able to see it. Maybe I'm wrong. Maybe I'm missing something. Right?
No,
Because
I guess
it like a 0.4% just from CMB at best. So I somehow doubt that you could, but maybe I'm wrong. Sorry, you were saying something?
No, I guess you're right. So it's probably in a parameter space. It's not of interest anymore.
No,
well, I think it would be interesting to look beyond synchrotron, maybe even inverse Compton scattering or Bremsstrahlung off of mini-charged dark matter could be
right.
Could be significant. I've never thought about this here, Joseph. It's a very good point.
So, but anyway, Tomer, your papers go well beyond the instant paper approximation of ambulance chasing.
Say again. What do you mean?
It goes well beyond the instant paper approximation. So this is a big body of work already.
Yeah. I always find it so. So my conclusion is an honest conclusion. I was never sorry. So I do it every few years when I find something that is sufficiently exciting. But I was never sorry for chasing some ambulance. So you always learn something, and it's always a seed for new ideas. So,
well, I remember back in the day when I refereed Nima's paper on the Sommerfeld announcement for the Pamela interpretation. I mean, that spurred, sort of hundreds of new considerations, and I think for phenomenology, very important points.
But it was the key point there was not only the phenomenology, but the experimental program. There's such huge experimental program searching for dark photons.
Yeah,
and that it all started there.
And I think if we think about ambulance chasing in the remote past of physics, I'm sure we can find many, many good examples that would drive us back to the birth of quantum mechanics, probably, when folks were trying to explain emission and absorption spectra. I mean, that was pure ambulance chasing if you think about it. So it's a blessed practice.
The whole flavor program is also benefited a lot from many ambulances along the years.
Absolutely.
And you will get them out, yeah. No, because many times we get blamed for doing this, having this practice of writing the paper in 2 weeks, right? It's I mean, there are bad things about trying to write a paper so quickly, but you always gain something too. That was the point. Yeah.
Do you mind if I ask you a question, given your experience on the 21 centimeter anomaly and the xenon 1 ton anomaly, given that you follow them closely? What do you think are the most compelling BSM solution, meaning if there are real signals? What do you think? Maybe any of your attempts or any others? I don't know.
I think it's, both of them are just very, very unlikely to be new physics. So 21 centimeter, I mean, do I believe that anomaly? I mean, probably not. It's a first measurement of this kind, and it's just very likely to settle down close to the standard model. So I very much doubt that the explanation is dark matter cooling or this Rayleigh Jeans kind of change in the spectrum, the CMB spectrum. I just doubt it. With the xenon 1 ton, it's a possibility, again, very unlikely in my mind. I don't find it very, very attractive. It's a fun game, but it's if I have to bet, I would not bet for
let me share the question. You don't believe in them because of the experimental result, because it's hard to measure or it's unlikely, or because of the theory developed ideas? That my question was more on that regard. Is there a theory compelling, something very compelling for any of them? You see what I mean?
Yeah. So for the 21 centimeter, I don't find anything very, very compelling in terms of I like the models that I've been working on, but I don't find it compelling for the purpose of explaining 21 centimeter. For xenon 1 ton, it's much easier. It's much easier. And exothermic is a possibility, and there are so many games that you could start playing, and even absorption is a possibility. So it's not that I don't. So I find these models compelling, very possible explanations, but the experimental situation is such that I very much doubt that this is new physics. I very, very much doubt. And again, even with the xenon 1 ton, remember that you need this very special case where you see it only in 2 to 4 keV. This is very, very special. This is not what I would naturally expect, and you need to do some loops in the air to do that. You can quite easily, but still. There was only one anomaly that I truly believed, and that was the 750 GeV. That was the one time I actually believed it's real, and of course, I was completely wrong. And my colleagues were telling me I'm wrong, and I was somehow naive. But yeah, I think that the models are very interesting, but they're not interesting for that anomaly. They're just interesting because they can do other things for you. And yeah, the one thing I'm excited about is the mediation scheme, for instance. The chameleon-like mediation scheme. I think they just open up a whole new set of models that you could play around with. Is this nature? Only God knows. I mean, I doubt it, but who knows? But so I'm excited about the models. I'm not excited about the explanation for the xenon 1 ton. Yeah.
Wonderful. So
thank you.
Jan has had his hand raised very diligently for a long time. So go ahead.
Yes, hello. This question is directed to Tomer. Yeah, so I'm just have a curiosity regarding the explanation for the edges result. So it seems that you're going in the direction of trying to cool down the gas to explain the very low, spin tip temperature. So, but then you can also go in the direction of heating up the 21 centimeter photons, right? So, what's the status of this? Or I guess somebody has already done this.
Sorry, I'm not totally sure I understood the question, because in the cooling, in the scenario I was describing, we are just cooling down the baryons directly. Yeah, we're not touching. Did you mention maybe heating up? Is this what you mentioned?
Photons, like the other option of explaining the edges result. So maybe can you have like dark photons oscillating into ordinary photons? Like, it's a very naive idea, but do you think it's also viable?
Yeah, I think it's viable. I think that for a while it was the only viable solution, because the milli-charge wasn't working until I think basically this paper that I mentioned that we wrote. I think the milli-charge wasn't really working except a tiny sleeve in the parameter space, whereas the changing the CMB was perfectly fine. I think it still is. So yeah, both ideas are now viable, as far as I could tell. Yeah. Was this your question? Or?
Yeah. It's actually what I had in mind. I'm also curious about how this would pan out in the recent, Xenon One-Ton XS. Somehow you combine these two constraints that you get from these two things.
So the reason I did, one of the good things, honestly good things, that to talk about work in progress is that I've been really inefficient, and because of family around me in the COVID-19 situation. So, and I took this week. I've decided that I'll talk about things that are not done yet, which means that I got all of my colleagues to work with me and push forward some projects that have been stuck for a while. And I was really hoping to show a plot today with that, whether, I showed that plot that shows you the region in parameter space that may explain the xenon, but we don't have that plot yet. And the reason we don't have that plot is that for whatever, I don't know what happened, but my cluster, I have a cluster at Tel Aviv University, and all of the files, the simulations for solving these differential equations and so on are actually pretty extensive. And there were lots of files that were saved there and everything was deleted. So we'll need a few more weeks now to reconstruct them, to do it again. So I don't have a plot for you. I'm sorry, I don't know which region of the parameter space would actually end up working, but
looking forward to those results.
Yeah. So have we. We've been stalling with this paper for way too long. Yeah, in fact, never mind. The diffusion of milli-charged particles, we started working on it 2 years ago. So it's been a terrible ordeal trying to get it out. Yes, I don't know the answer. I promise to have it soon.
Thank you.
I have a question actually for Sergio. No, I see that Sergio, you're back. Can you hear me?
Yes, can you hear me now?
Yes. So just out of curiosity, you talk about these WUMPs, something like this, weakly unstable massive particles or so. That's just decaying dark matter, or it's something?
Yeah, that's just the name for decaying dark matter. But that was a name that was coined in '89 and just followed up by a couple of papers after that. The name never got stuck in the community. So it's just decaying dark matter.
And you just want to revive it, or what?
Well, I liked it, so. So actually, why decay in dark matter? Why WIMPs, and why do you use WIMPs for annihilating? When you talk about annihilating dark matter, you say WIMPs or whatever. It doesn't matter. It was just a fun fact.
Okay, thanks.
So I couldn't be here on the discussions in the past 2 days, which I apologize for, because family around here is it's the worst time around here. But was there a discussion about self-interacting? I guess Haibo is not here anymore, right? Was there a discussion about this diversity and self-interaction? Does anyone understand? I'm wondering whether there were claims in the past that this Haibo had these papers also about the baryonic Talley-Fisher, diversity, and I'm wondering whether self-interaction really explains these things better than, or is it just a fit? It's a good fit, and it's a somewhat predicted fit, but I don't know. I don't understand well. I'm not convinced yet that this is a model. Certainly not with the baryonic Talley-Fisher, because it could explain the baryonic Talley-Fisher. I don't think it predicts it in any way. I'm wondering if anyone has a thought about this, or if you discussed it 2 days ago. I started asking, but then there was no time and I could stay for the discussion.
But I think we would discuss that explicitly. But I think his point is that, yeah, such interactions can basically explain all this tension. But I mean, it really depends whom you're asking, because last week we had this talk by Julio Navarro, and he had a strong point saying that there's no problems or no even tension with the Lambda CDM whatsoever. So I don't know.
Yeah, I know. I heard this
kind of
talk.
Yeah.
So go ahead.
No, that's what I want to tell. For this, I don't have a strong opinion on what I mean.
Yeah, I never understood Navarro's point in terms of really explaining the baryonic Talley-Fisher. It requires a lot of feedback, which is model dependent, and they don't really know how to model it. So it's possible that there's no tension, but we simply don't know. And I think that's Navarro's point, at least the talk that I heard him give, that we simply don't know, and that's a fair point, whether there's tension. These are exactly those regions where we don't yet understand the simulations well enough. But so I think that's fair. But the statement that self-interacting dark matter is explaining baryonic Talley-Fisher, for instance, that I think is, I don't understand why that's true. I wanted to, I don't know. I wonder if anyone else. At the end of the day, they fit to the asymptotic velocities and the central density and the concentration parameter. And I don't understand. So it seems to fit, but it doesn't explain why there would be this correlation, which everyone sees. So, anyways.
My impression from Haibo's talk was you could get any curve you wanted with self-interacting by changing the parameters. He was showing these different figures, and basically you could get anything you wanted.
Right. I think
maybe Shoyoung, if you know more. So you're muted.
We can hear you. Yeah.
Okay, sorry. Yeah, I think. Physically speaking, the general idea is with self-interaction, dark matter could summarize with itself. Then the baryonic contraction would affect dark matter as a whole more efficiently. I think this is the general idea. So if you have more baryons in the center, it could get a very dense core. So if you don't have baryons, you could have shallow profile. So this would kind of explain the diversity. But this
right.
is like
really,
a late understanding.
But you see, the point is that the way I understand it, it really goes back. So the diversity is thrown onto the whether you have diversity in the baryonic density with respect to the dark matter density, right? Because in the end, if you have an isothermal profile, you depend on the density that may be dominated by baryons or by dark matter at the center. And it says there's diversity there, right? That's the idea, if I understand it correctly. And
yeah,
you have to.
I think his claim is like with self-induction, the baryon could affect the profile more significantly than cold dark matter. So you would have larger diversity in the SIDM than in the cold dark matter case.
Right, given the diversity in baryons, in baryons.
Yes.
And for that, somehow you still need some correlation. Well, for the diversity, I don't know, but it certainly is not discussing anything about the baryonic Talley-Fisher here. So the connection between how much baryons you have at the center and what is the halo profile, what does the halo profile look like, right? And why do you have these rotation curves the way you see them? That is not explained here with the diversity problem, which is fine. It's a different problem, but you still need to somehow. To me, it sounds like what the statement is that as long as you have diversity in the baryonic density in the center, you would also have diversity in the cold dark matter profile, which I accept. I think that's a valid point. It's not clear to me how predictive is the model. And the bottom line is that they fit the parameters. So they take each plot and they use the asymptotic velocity, and they have two parameters for each plot like that. They would have the asymptotic velocity and they have the concentration parameter, and then they have one parameter for the velocity for the cross section, self-interacting cross section, right?
Yeah, the materials.
So how predictive is it? I can imagine that it's better than MOND. I think that's the statement, and I believe them. It's better than MOND. The diversity is better than MOND. But how, well, anyway, how predictive is it? I still don't understand well enough.
I think the main issue is this massing concentration factor. I mean, simulation would give you a range, then you need to tune it. I think it's around, I mean, it's within the range. It should depend on the history of this halo, so it's not extremely predictive.
Right. Yeah.
It just chooses a value allowed by simulations, but it's kind of free.
Right. Yeah. Anyways, I still don't see a way of. The reason I'm intrigued with the baryonic Talley-Fisher is because it shows, it shows a correlation, which is no matter what happened, I still haven't got, I never got a very clear, other than MOND, which gives you a very clear, there's no theory, but it gives you a very clear reason why there's this correlation, simply because there's no dark matter. So we all know that MOND doesn't seem to be working on various scales, and well, I'm not going in that direction. But other than that, I've never seen a truly convincing explanation.
I guess not. I mean, I think the general feeling in dark matter community is, Talley-Fisher relation applies to galactic size halos. So probably at that, several orders magnitude, those kind of halos has one self-regulating mechanism to make it fit that way. I think Carlos Frank had a paper basically on, simulation, they show it works, but of course in dark matter community, we don't understand it analytically.
Right. Yeah, Manoj Kapingat, and I forget who else, also had this paper long ago. I should find it, claiming that it's CDM should be able to explain it, but even I didn't understand it well enough to figure out what is the mechanism that causes it. Why is it so close to 4, right? We don't know that it's 4, but it's very close to 4.
And this is where MOND is mostly successful.
Yeah. Yes. Well, that and the universality, yeah. The mid-Rome acceleration, which seems to be universal.
Yeah, I think at small scale there are some. I mean, we just say there's some self-regulation, maybe from you have a galaxy, you form a massive black hole in the center, then there feedback. They're just I mean, in the end, it's stable. It becomes stable at some point. Miraculously, it fits this scaling.
Right. Right. Yeah. Anyways.
Cool. So, Nicolas, how are we doing on time?
Well, I think there are no constraints, but I don't know if there are more questions or comments.
We are unbounded from above. Very good. Any more questions, remarks, thoughts?
I think perhaps shall we thank Nicolas for putting all this together?
Yes, we really should. Thank you so much, Nicolas.
Thank you.
Thanks.
Good job. It was really fun.
Next time in Brazil, yeah?
Yeah, we hope so. The same discussion,
but real Brazil, yeah. All right. Thank you all.
Yeah.
All right, guys. Thank you very much.
Cheers.
Thank you.